Hi everyone, hope you are safe without any issues and safe at home. So far we've been discussing about the circuit analysis, where we actually wanted to find out all the details of the circuit, like the voltages, many currents of the branches and so on and so forth. So we used several techniques or methods like branch current analysis, mesh analysis and nodal analysis. Different techniques being used for different situations of the circuit or different topologies of the circuits. However, we wanted to find many details of the network. Today we will start the discussion on network theorems, where we have a set of theorems that we are using, namely the superposition theorem, Thevenin's theorem, Norton's theorem, and maximum power transfer theorem. In this case, the situation is a little bit different from the previous techniques. That is, earlier we wanted to find out all the details of the circuit, but here in each case we are concentrating on a particular aspect. So let's start with the superposition theorem. This is a technique which we can use if we are interested of finding the voltage or the current of a single branch or a single element only. Now if you want to find a particular detail, like let's say you have a resistor and you want to find the voltage across or the current through the resistor, using mesh analysis, nodal analysis and analysis things like that is actually a waste of time, because we don't want the other details to be found. In this case, we can use the superposition theorem, which will help us to find the details about one element or one branch only, right? So when you use mesh analysis or nodal analysis, we'll have to find details, or we have to use multiple equations and solve them, as you saw in last week. That is not necessary in this case. The theorem says the total current through or voltage across a resistor or branch may be determined by summing the effects due to each independent sources. We know that we have multiple sources in the network. If we had one source, then the method is straightforward, like what we discussed in the beginning, early stages. But when you have multiple, we can consider one source by source and then find out the value that you want to find. Let's look at what we need to do. So now when you consider one source by source, we'll have to disregard or remove other sources. So what do you have to do in the case of removing a voltage source and a current source? When you remove the voltage source, we actually get rid of the voltage effect only. So an ideal source has an internal resistance of 0. So when the voltage effect is not there, the internal resistance has to be there in the place. So an ideal voltage source will be replaced by a short circuit. In the same way, a current source will have an infinite impedance. So when you remove the current effect of it, the effect of the current source or effect of the current supply of that source, you will end up with an open circuit, because the internal resistance is infinite. So it's like open circuit. So this is what we have to do for the other sources that we are not considering at a particular stage. Let's take this example. We have two sources in here. One is a voltage source and the other one is a current source. The question says determine the current in the load resistor RL. Verify the superposition theorem does not apply to power. Let's take this circuit and see what we can do. So So this is our circuit. We'll take one by one, one source by one source. So first case, taking the voltage source only. Right? If you take out the voltage or take out the current source, so considering the E only, so let's consider E only. We'll have to replace the current source by its equivalent. So it's an open circuit. I'm going to draw the equivalent circuit after removing I. We have E here, and I'm going to draw it like this to indicate that we have removed the current source, and then we have the load resistor of which we want to find the current. So let's label this as I1. Now this is R1, which is 24 ohms. E is 20 volts, and RL is 16 ohms. So now once you remove the current source, you see a circuit which is a closed loop, and I1 is the current that goes to both the resistors. So we can write I1 is equal to 20 divided by 24 plus 16, which is in amperes. This will bring us to, let's take the calculator, right, it's 20 divided by 24 plus 16, which is 0.5 amperes. So that's 0.5 amperes. Unfortunately, you are not here with me, so that you could have done the calculations with me, right? And that was actually help for me. But now me alone doing the lecture, so well, I had to do all the calculations, right? Now the second case we'll consider I only, and we get so we have to remove the voltage source, which will become a short circuit now. So there is a short circuit here now. I'm going to draw it like that, and the current source and the load resistor is there. So I is 2 amperes, and this is R1 24 ohms, RL 16 ohms. There's a short circuit there, and let's label this as I2. And now you have a current divider. There is this R1 in parallel to the current source, as well RL in parallel to current source, so we can use the current divider rule. So using current divider rule, I2 is equal to the other side resistance, that is 24 divided by 24 plus 16 into 2, and that is actually minus because the current source is in that way, and the current actually will go upwards through RL, but the current we have marked is downwards, so it's minus. Now the value here is 24 into 2, 24 into 2 divided by 24 plus 16, which becomes 1.2 amperes. which is negative, so minus 1.2 amperes. Now the superposition theorem says, right, using superposition theorem, IL in this case, IL is I1 plus I2, which is 0.5 minus 1.2 amperes, which is minus 0.7 amperes, right? So it's actually upwards 0.7 ampere current that goes through it, right? So now you see that you don't have to well, let's save this. Where do we have to save it? Right, so you didn't have to solve multiple simultaneous linear equations, but you just use the other techniques, some manipulations. I mean, keep in mind that, okay, when you are using superposition, why the purpose that you use superposition theorem is to avoid the complexity of the mesh analysis, nodal analysis, likewise the circuit analysis techniques. If you want to find only one parameter, maybe a voltage or a current of a particular device or a branch, so in that case you don't have to use mesh analysis, nodal analysis, branch current analysis and things like that, which are complex processes. So keep in mind, if you are using superposition theorem, there is no need of using other theorems or other techniques like the circuit analysis techniques. If you use them straight away, you use the circuit analysis techniques instead of using superposition theorem. So if you use superposition theorem, avoid using other circuit analysis techniques rather than using simple techniques like voltage divider, current divider, Ohm's law, and so on and so forth. Right, so here you can see actually the process shown in here, right? 0.5 and 0.2, so the answers that we got are correct. Now when it comes to power is I squared R, because we found actually the current, so we can use the form out of the three equations for the power. We can use P is equal to I squared R. If you apply that, we can see that for the first case, that is using the voltage source only, the power becomes 4 watts, and using the current source only, the power becomes 23.04 watts, and the addition of those two becomes 27.4 watts, 27.04 watts. However, the actual final power dissipation becomes 7.84, which is not equal to the value that you get in this place. So that does mean that for power you cannot use the superposition theorem. So what you need to do is to use superposition theorem to find the voltage or the current of a particular branch or an element, and then use the power equation to find the power. So you can't use this superposition theorem to find the power, or superposition theorem doesn't work for power. A second example, determine the voltage drop across the resistor R2 of the circuit. So let's take this circuit. Okay, let's use a new page. Right, so in this case as well, in this case we have three sources actually. We have two voltage sources and a current source. So I'm going to take one by one. What we are supposed to find is the voltage drop across the resistor R2. So that is this resistor R2, and let's take one by one, consider E1 only. So if you consider E1 only, our circuit becomes, so you have the resistor here. Oops, what has happened there? Right, you have the E. Please don't mind the shapes, because not in a very comfortable situation like in the lecture hall. Right, so now you have this and this. Now the current source is removed, meaning that you have an open circuit there. I'm again drawing whatever the place that you have made or replaced the source to indicate that there was a source there, and this resistor. And E2 is also removed, meaning that there is a short circuit there. Right, so this is R3, 1.6K, and this is 1.6K again. Right, and yeah, this is R2. This is where we want to find the voltage across, and E1 is 16 volts and R1 is 2.4K. Okay, now we can see that I'll label this. What we want to find is V1, V1. So VR3 is ultimate target. So VR2 is ultimate target. So VR2 would be equal to the first one, V1, V2, V3, the addition of those two. Now in between these 2 points, what we want to find out is the voltage across these 2 points. So we have to find the voltage between these 2 points, where you have this R2 and R3 parallel. So V2, we can write V2 as the resistance here. We can use the voltage divider rule. That is 1.6K parallel 1.6K divided by that 1.6K parallel 1.6K plus 22.4K into minus 16 volts. Now when you put two resistors in parallel, the resultant will become half of that. So 1.6 divided by 2 is 0.8K. So 0.8 over 0.8 plus 2.4 into, that is minus, whole thing is minus 16 volts. So let's use the calculator to find this out. So 0.8 into 16 divide by 0.8 plus 2.4, that becomes 4 volts. Minus 4 volts. Now let's take the second source only, that is consider the second source is I only. So if you consider the I only, so we have a voltage source here which is now short circuited, and we have a current source here and a resistor here. There is a resistor here and then a current source here, this is 5 milliamperes, I is equal to 5 milliamperes, and then we will have the resistor here and a short circuit. So 1.6k, and this is also 1.6k, and this is not there, and this is 2.4k. Now we will have to find the voltage across the 1.6k resistor. Actually all the three resistors are in parallel to each other, so we can use simply the the Ohm's law, right, using Ohm's law. The voltage that we want to find is the voltage here, which we will label as V2. So V2 is equal to V2 with note that this resistor is in parallel with this resistor and is in parallel with this resistor, so it is a total resistance. V is equal to IR. So I is 5 milliamperes, 5 milliamperes into, we have a parallel resistance 1.6k parallel with 1.6k parallel 6k parallel with 2.4k. Let's resolve this separately. So 1.6k parallel with 1.6k is 0.8k. So therefore 1.6k parallel 1.6k parallel 2.4k will be equal to 0.8k into 2.4k R1 R2 over R1 plus R2. So that is 0.8k plus 2.4k, which is, if you use the calculator again, 0.8 into 2.4 divided by 0.8 plus 2.4. So that is 0.6k, so 600 ohms. Now V2 is 5 into 10 to the power minus 3 into 600, which is let's find out what is 5 into 600. 5 into 600 is equal to 3000, which means the value voltage is 3 and that is plus. So 3 volts, the second case, V2 is 3 volts. Thirdly, we will consider only the 32 volts voltage, that is E2. So consider E2 only. Now we have a voltage, so we have a short circuit here, so I'm going to draw it in the same shape as what we have there. So we have a resistor here and we have another resistor here, short circuit in here, then the current source is open circuited, and we have a resistor and a voltage source here, that's 32 volts E2, 32 volts if I'm correct, yeah. Then we have 1.6k here, and here we have 1.6k, and then 2.4k. Okay, here. Now again we have a voltage divider. Here the voltage that we want to find, V3, is this. You can see that this resistor and this resistor are in parallel, and we want to find the voltage across these two. So V3 is now equal to 1.6k parallel 2.4k over 1.6k parallel 2.4k plus 1.6k, that is this resistor, into 32 volts. Now what is this 1.6k into 1.6k parallel 1.6k parallel 2.4k is 1.6k into 2.4k divided by 1.6k plus 2.4k, which is, let's look at the value, 1.6 into 2.4 divided by 1.6 plus 2.4, 0.96k. Sorry, 0.96 is a ratio, right? Sorry, this is k. Now V3 becomes 0.96k divided by 0.96k plus 1.6k into 32 volts, which is 0.96 into 32 divided by 0.96 plus 1.6, which is 12 volts. So now, using superposition theorem, VR2 is equal to V1 plus V2 plus V3. V1 is minus 4 plus 3 plus 12, which is equal to 11 volts. Right, so the voltage across the resistor R2 in this circuit is 11 volts plus. Let's save this. Right, let's look at the answer in here. Right, it's minus 4 plus 3 and then 11. So the result is correct. Right, so that is if you want to find the current through a single resistor, a single element or a single branch, or the voltage across a single element or a single branch. You can use the superposition theorem instead of using circuit analysis techniques like the branch current analysis, mesh analysis and the nodal analysis. Which consist of simultaneous linear equation solving, but in the superposition theorem you don't have to do that. You consider a source by source, as one source at a time, and the theorem says that the total effect will be the addition of each case, algebraic addition of each case. Now the next is the Thevenin's theorem. Now in this case, in this example, let's look at the theorem a little bit later on. Now in this case, if you want to find out the current through or the voltage across this RL at different RL values, now you can see that the RL is a variable resistor and you want to find the current through RL or the voltage across RL at different RL values, as you can see here in In this case they have said as RL equal to 0, RL equal to 2k and 5k. Now if you are using mesh analysis, you will have to perform mesh nodal, you have to perform that 3 times, which is far too difficult. Even if you use superposition theorem, you will have to use the superposition theorem 3 times, perform superposition theorem 3 times to find the value, the current maybe, in this case it's the current through RL at 3 different RL values. Now what if we can model the rest of the circuit as a voltage source? Then you will have, that is you model this whole thing as a voltage source, and then you will have a voltage source connected to the resistor, so you can play with it very easily. So that is actually we will deduce the whole circuit or the rest of the circuit as a voltage source in series with a single resistor. Once you do that, then we do this actually when you want to find out the value or the current or the voltage of a element at different conditions, like what is shown in this example. So the Thevenin's theorem says any linear bilateral network may be reduced to a simplified 2-terminal circuit consisting of a single voltage source in series with a single resistor, as shown in the figure. So basically what we do is we model the entire circuit as a practical voltage source, a single practical voltage source that is referred to as the Thevenin's voltage source and the Thevenin's resistance. So any practical voltage source should have an internal resistance, and then you have a voltage source. So voltage source in series with a voltage source in series with a resistor is actually a practical voltage source. Let's see how we can do this. Now once you model the circuits like this, now the resistor will be connected in here. If you want whatever the different value that you need, just put that as RL and derive the equation for the voltage or the current across that RL, and substituting different values to RL, you can get the value that you need. So that becomes very easier once you derive the Thevenin's equivalent circuit. Now there are several steps again we have to follow. First step is that we remove the load from the circuit, because we consider the rest of the circuit and we derive the Thevenin's equivalent for the rest of the circuit by removing the load. Now load is the resistor across or through which we want to find the voltage or the current. So the second step is label the resulting terminals. Labeling is not actually mandatory, but to make it easier, you can label them as A and B, or any 2 letters you prefer to. Then set all the circuits, all the sources in the circuit to 0, meaning that voltage sources will be short circuited and current sources will be open circuited. And determine the Thevenin's equivalent resistance RTH by calculating the resistance seen between the 2 terminals. So if you measure the resistance between the 2 terminals in this circuit, once you remove all these sources, that will be the Thevenin's resistance. Then you replace all the sources again and try to find the voltage across these 2 terminals when you don't have the load. So it's open circuit situation, right? And in this case you may have to use superposition theorem if you have more than one component or more than one source in the circuit, right? So once you do that, you can replace the entire rest of the circuit excluding the load resistor or the full circuit other than the load resistor with the Thevenin's equivalent. Now let's look at this example and see. This is the same example that we were talking about. So determine the Thevenin's equivalent to the resistor external to the resistor RL for the circuit of the figure. Use the Thevenin's equivalent circuit to determine the current through RL. So let's take this. The first thing that you have to do is to remove the load. So that's after the load is removed. Then what you do is you let's take this out. So this is after the load is removed. Now from this, the next step is you have to remove all the sources. So once remove sources. Once you remove the sources, you get the resistors only. So this is a short circuit, and you have a current source, that's an open circuit, and your two terminals are A and B, and look into this, and this is RTH. So in this case RTH is equal to, this is 24 ohms, so directly 24 ohms. Then what you need to do is to replace the sources again, that is you take this one, and then you try to find out the voltage across the two terminals A and B. So when you do that, we know that the current in this, so now you take this thing again, and you know that the current in this loop is 2 amperes because you have a current source here. So we have a voltage here which is equal to 24 into 2 volts. So now what is VAB? Thevenin's voltage ETH is equal to VAB, which is 20 minus 24 into 2 volts, which is 20 minus 48, which is minus 28 volts. Now that is the voltage Thevenin's equivalent. So we will label this as ETH is now negative, so we will mark it like this, and RTH is in here, and the RL. So RL is 16 ohms if I am not mistaken. Where is that? The RL is 16 ohms, and we have 24 ohms here, 24 ohms here, which is R1. Sorry, RTH is 24 ohms, that is this one, and ETH is 28 volts, and I have got rid of minus now because I have placed the voltage in the appropriate direction. Now what is IL? That is what we are supposed to find after doing that, current through IL. So I am going to mark the current downwards, IL. So IL is minus ETH over RTH plus RL using Ohm's law. So that is minus 28 divided by y minus is because the actual current would be going upwards, and the current that we have marked is in the downward direction. However, if you want to mark the current in upward direction, there is no issue in doing that. 24 plus 16, which is minus 28 divided by 40. Well, let's avoid this step. 28 divided by 40, which is 0.7, right? Minus 0.7 amperes. So this is the same current that we had in the previous example, right? Now using Thevenin's equivalent. However, we are using Thevenin's equivalent, although in this case we used it for a single situation. We usually use it for the situations where you need to change the values and redo the calculation again and again. So this shows that the current is upwards. The second example, okay, let's take this one. See, find the Thevenin equivalent circuit excluding the load of the circuit below. Using the equivalent circuit, determine the current through the load resistor when RL equal to 0, RL equal to 2 kilo ohms, and then RL equal to 5 kilo ohms. Now you can see this is a situation where you need to perform the calculations 3 times if you were using the superposition theorem. Now let's take, right, let's take this and see. So this is the circuit that we need to find the Thevenin's equivalent for. Oops, that's too large, right? Okay, let's take this. Now first thing that you need to do is to remove the load, right? So by removing RL, you get remove the load. By removing that, you get the simplified circuit that's excluding this. Okay, I'll play a little trick here. I'm going to copy this. Okay. Oops, it didn't copy it. Why is it so? Okay, let's right. So we have the voltage source, then the current source, sorry, the resistor, and the current source, and there is another resistor here. And let's label this as A and B. This is R2, 2 kilo ohms, R1, 6 kilo ohms, E, 15 volts, I, 5 milliamperes. Now the next step is you remove all the sources, right? Remove sources. Once you remove the sources, you get this resistance, and this becomes a short circuit because it's a voltage source, and this becomes an open circuit because it's a current source, and there is another resistor here, point A and point B. This is 2K this is 6k, and you want to find the resistance R TH here, the Thevenin's resistance, which is equal to, you can see that the two resistors are in parallel, so it is 2k parallel 6k, which is 2 into 6 divided by 2 plus 6 kilo ohms, which is 2 into 6 divided by 2 plus 6, 1.5 kilo ohms is the Thevenin's resistance. Now you need to find the Thevenin's voltage for the circuit that you got in here. This will be VTH or ETH, the Thevenin's voltage value. Because we have two sources in here, we will have to take one by one, right? So to find ETH, we first use consider what is that? The source is E only. When you consider the E only, we have the voltage source here and the resistor here. The current source is open circuited. There is another resistor here, and you find the voltage across these 2 points. This is 2k, this is 6k, and what you have here is 15 volts. E is 15 volts. So let's label this as ETH1. This is A, this is B. ETH1 is equal to, can use the voltage divider rule, 2 divided by 2 plus 6 into 15 volts, which is 30 divided by 8. 30 divided by 8, 3.75 volts ETH1. Then consider I only, right? If you consider I only, you have a 6k resistor here, then this is a short circuit because it's a voltage source, and you have a current source. I can't remember which direction it is. Let's look at. The current source is upwards 5 milliamperes, so it's upwards I 5 milliamperes. Then you have a resistor here, 2k, 6k, and you need to find a voltage across A and B, which is ETH2. Now you have a current source, you need to find the voltage there. You can see that this resistor and this resistor are in parallel, so the voltage across both these resistors is what you actually find across these two values. So it is 2k parallel 6k into 5 milliamperes is what you get. So this will result in a kilo ohms resistance. This is milli, so I can get rid of those two. So we can write it as 2 into 6 divided by 2 plus 6 into 5 volts, which is now, okay, we actually found this value, right? Like 2 plus 2 2k parallel 6k is 1.5k, so it's 1.5 into 5, which is 7.5, if I am not mistaken. 1.5 into 5 is 7.5, and that's also positive. yeah, because the current goes downwards in here, so it's 7.5 volts. Now ETH, using superposition theorem, ETH is ETH1 plus ETH2. ETH1 is 3.75 plus volts plus 7.5 volts, which is 3.75 plus 7.5 is 11.25 volts. So the Thevenin's equivalent now is we have a source and we have a resistance. The source is ETH, the resistance is RTH, and we have a load RL, right, which is actually variable. RTH, the Thevenin's resistance, is 1.5K, and ETH is 11.25 volts. Now the question: at three different values, RL equal to 0, we want to find the current through. So let's find the current through as a function of RL, IL, right? So now IL is equal to, okay, you can use Ohm's law, ETH divided by RL plus RTH, right? Now if RL equal to 0, IL is equal to ETH is 11.25 divided by 0 plus 1.5K, which is equal to 11.25 divided by 1500, which is, if you multiply by 1000, you get 0.75 milliamperes. 0.75 milliamperes. Now if RL equals what you have here in the second case, 2K, 2 kilo ohms, then IL is equal to 11.25 divided by 2K plus 1.5K, which is 11.25 divided by 3.5, that is 3. Is this correct? Let's check. Okay, 3.21 milliamperes. Let's check if this is correct. 11.25 divided by 1.5, which is 7.5 actually. So this is 7.5 milliamperes. 7.5 milliamperes, and in this case it is 3.1K, and then if RL is 5K, IL is you substitute 5 in here, so it will be 11.25 divided by 6.5. That's 1.73 milliamperes. So now you can see that any different RL value you can calculate the current through without performing any further analysis, simply by using this particular equation, right? That is using Ohm's law, right? You substitute different values with for RL, right? So 1.5K remains unchanged, which is the Thevenin's resistance. This is unchanged, but this can change. So that makes our life easier. But if it is only one parameter across one element only, so what you need to do is to remove that element and consider the rest of the circuit and find out the equivalent Thevenin source, Thevenin's equivalent for the circuit excluding that particular element, which we treat as the load, and then you find out all the parameters. So that's the derivation. Let's check if our results are correct here. 11.25, and the 3 currents are also correct. So we've done it. Now that's all for today, folks. The next week we will look at another option, that is the Thevenin's Norton's equivalent, where now in the Thevenin's equivalent we converted the circuit into a voltage source and a current and resistor. In the Norton's we will be converting the circuit into a current source. Now in here today we converted it into a voltage source and a series resistor. In the Norton's it will be converted into a current source and a parallel resistor. So let's look at that, as well as the maximum power transfer theorem, in the next lecture. Have a good time. See you.